Now that you're comfortable with arithmetic sequences, we will start looking at geometric sequences. When you come to do questions on your ISU quiz, you may have 3 or 4 sequences in one question. You're asked to determine what type are they. So first let's look at this one. Let's see what makes this not an arithmetic and what makes it a geometric. If it was arithmetic, we would be increasing by a constant difference each time. Just doing a quick check, when I subtract 30 from 6, I would get negative 24. When I subtract 6 from 1.2, I would get a different answer of negative 4.8. So there is no constant difference here, so that sequence is not arithmetic. What makes it geometric? The first term is 30. The first term in this sequence is 30. The A equals the first term is the same for arithmetic and geometric sequences. What makes this a geometric sequence is, by definition, there is a constant ratio. I multiply 30 by a value to get to 6. I multiply 6 by that same value to get to 1.2. I multiply 1.2 by that same value to get to 0.24. And to determine that value, which we call the constant ratio, we take the 6 and we divide it by 30, giving us a value of 0.2. We then take the 1.2 divided by 6, giving us a value of 0.2. So we now, as we see this pattern evolving, we now can say with some certainty that we have a geometric sequence and the constant ratio is the value 0.2. So that is my constant ratio. And once, as mathematicians, we've seen a pattern, we try to define it with a formula. And so for a geometric sequence, the general term is the first number multiplied by the constant ratio to an exponent, and it's n-1 exponent, because to get to 6, which is term 2, we only multiply the 30 by 0.2. So we have now defined a general formula, which of course you will memorize. What happens if we want to get a general formula for the precise sequence above? We start off with the general formula for all geometric sequences, and then we personalize it for our sequence. Our sequence had a first term of 30. So I am going to come over here and I am going to make my first term here 30. So Tn for my sequence equals 30. And now I'm going to multiply by my constant ratio 0.2 to the n-1. And that is the general term for the specific sequence that we're using in this example. It is 30 times 0.2 to the n-1. Let's take it one step further. Let's be given an n value. So if we want T20, if you're asked to determine T20, we're actually telling you that n equals 20. That's what we're saying precisely. Hey, here's your sequence n equals 20. Determine what this is worth. So I'm taking it from up here. We're always going to start off with 30. So that will be A times r to the n-1. A times 0.2 to the 20 minus 1, because I'm looking for T20. Of course, I'm not going to leave it at that. I'm going to do that n-1 and make it 30. And again, remember, you always have your equals here. Make it nice form, okay? So I'm going to go in here and I'm going to put my equals right in front of my 30, because that's good mathematical form. So I've got 30 times 0.2 to the 19. Now at this point, if you could evaluate it, you would. You would evaluate it using your BEDMAS, which means you would do your exponent first, and then you would multiply your answer by 30. However, when I come up here to evaluate decimal 2 to the exponent 19, this is my answer. Incredibly small. So when you get into numbers that are so small or so large that it takes you more than 8, 9, 10 digits to write them, I would be quite happy if you would leave your answer like this. That would be just fine. Now, Moving on to the last thing that you will be asked to do in your ISU, and that is we will give you a sequence. There will be a gap in the sequence and we'll ask you to determine how many terms are in the sequence. So again, working with the sequence above, we are asked to find how many terms. This is what we know. We know the last term is 0.00192 and we know the general term. And what we will now do is we will set up an equation between the two. We will take our general term, which is 30, times 0.2 to the n minus 1 technical difficulties, I appreciate the patience. So our Tn is 30 times 0.2 to the n minus 1, and then I will set that equal to 0.00192. So I'm going to make that equal to the last term that we're interested in, 0.00192. Now, we have an equation. We're good at solving equations. To isolate the power, what will I do? I will divide both sides by 30 so that I isolate the power. So the left side gets divided by 30 and the right side gets divided by 30. So, having done that, we will get this 30 cancelling, and we will end up with just the 0.2 to the n minus 1 on the left side of the equals, and on the right side of the equals we will have the value when these two are divided. So when I divide these two, my answer is 0.000064. And this is where you need to have your scientific calculator at the ready, because we are actually going to now try to solve this equation, and a calculator will prove invaluable for that. We solve with the system of guess and check. So right now we have to guess and check. 0.2 to an exponent equals 0.0064, and we have to guess the exponent. When you're in grade 12 you'll do this with logs, but right now you're guessing and checking. Let's try to the exponent 4. Oh, that's too small. Let's try to the exponent 5. Nope. Let's try to the exponent 6. We're getting close. There we go. Okay, so I now know that this value 0.000064 is in actual fact 0.2 to the exponent 6. So I'm going to set up that equation. I'm going to make that equal. So this is what I'm now saying. I'm now saying that my 0.2 to the n minus 1 is in actual fact equal to my Okay, so all we've done here is we have rewritten this number as a power. Now we have equality of powers. If we have two powers that are equal and they have the same base, it follows then their exponents have to be equal. So what that must mean is that the n minus 1 exponent on the 0.2 here, right here, must equal 6, in which case n must equal 7. So we have now established that 0.00192 is the 7th term, is T7. And that is our final answer. Can you check? Of course you can check. And of course I have checked because I wanted to be sure. And here is the check. This is the check for my final answer to make sure it was correct. T7 is 30 times 0.2 to the 7 minus 1, which is 30 times 0.2 to the 6. And let's get a calculator. And let's see if the calculator does BEDMAS. 30 times decimal 2 to the exponent 6 will give us 0.00192, the exact value we were looking for. So my final thought for you is that equals 0.00192 QED, quod est demonstratum. I'm very, very happy with that. Check mark. So, I hope this helps. The side column here, just ignore. That was me trying to be efficient, and I wish you good luck with your ISU.